Jai Hind. Myself Amita Asthana from AKGEC Ghaziabad. In this video lecture, we will discuss the third unit of KEC 302 Digital System Design, and the topic is flip-flop. So here we are going to discuss various types of flip-flops. So in the last video lecture, we have understood about the working of the SR latch, active high, active low. For both the cases, 4 configurations we have studied and understood, and how the SR latch gets stabilized, and the difference between the SR latch or any latch and the flip-flop is being that all the latches are level triggered, as well as all the flip-flops are being given some sort of clock. So here is the logic symbol for the SR flip-flop, that is S and R. We are having the 2 inputs, and the clock is going high at the the edge. As we can see, this clock is being given, and this flip-flop is getting triggered at each active high level of the flip-flop. Okay, so again there are 2 outputs, that is Q and Q bar, right? And the logic symbol is S. Set, again reset for R, Q the output and Q bar. Here again we are taking Qn as the initial output, Qn plus 1 as the next state output, and after considering the feedback, this is going to the feedback to the SR flip-flop. So whenever the clock is high, the SR flip-flop is functional. Whenever the clock is 0, the SR flip-flop is not functional, and it will remain in the same state of no change, right? So here the SR is 0 0 as the latch functions, the flip-flop also functions, only the difference is the clock is high, and this state is achieved only at the high level of the increasing level, positive edge of the clock. So again, for S and R to be 0 0, there would be a no change, and for 0 1 it will go to the reset state. For 1 0 it is going to the set state, and 1 1 it is going to indeterminate state, right? Now, so this is how we can represent the flip-flop. So this is the circuit. We are using 4 NAND gates, and the gates are G1, G2, G3 and G4. So one pulse transition circuit has also been added, so that it is active at the rising or falling edge of the clock. Whatever way we can give the clock, maybe at the rising edges or maybe at the falling edges. So here we have the same arrangement for the latches. One more we have added 2 NAND gates we have added to our SR latch, and that is the both NAND gates are connected to the clock in this way. Here the S and R being the inputs for this particular flip-flop, right? So again the table and the working is same for the flip-flop. Now coming to the D flip-flop. So D flip-flop we can make or derive from SR flip-flop. The only basic difference is D is known as delay flip-flop or data flip-flop. By the name you can understand that S is always inverse of R. That means there are only 2 possible inputs which we can give, that is maybe S is 0, then R will be 1, and if S is 1, then R is 0. So So there are only two possible inputs which we can give. So the table gets reduced and there are only two states. If the clock is high and D is equal to 0, the output will be 0 or reset here. And if the clock is high, D is equal to 1, the output is 1, 1, that is set. So this particular is the logic symbol for the D flip-flop, and the working is same as we have already discussed in the previous video. The now coming to the JK flip-flop, after having the discussion about the D flip-flop, coming to the JK flip-flop. So the SR flip-flop, the undesirable condition is this. This indeterminate condition is strictly undesirable. So how to remove this particular condition using the JK flip-flop, or how we can derive JK flip-flop from SR latch, that we need to understand. So coming here, the JK flip-flop, the indeterminate condition has been removed, as you can see, for clock high. For clock high and S is equal to 1, R is equal to 1, the previous output gets reversed or gets toggled. So this is how we can understand the function of the JK flip-flop. There is a toggle, that means for J and K to be 1, the previous output gets reversed. So this is how we can understand the JK flip-flop. There is a difference between SR and JK, that there are 4 conditions, obviously 0, 1, 1, 0, 1, 1. This is no change condition. This is for S and R. This is reset. This is set, and this is toggle. Provided clock is high. If clock is low, then there would be no change, as mentioned earlier. So what we do, how we make it the JK flip-flop from this SR flip-flop, what we do is, see, there is a little change, that this input, is being given to this G2, and this feedback is also being given to G1. These two connections converts the SR latch to, SR flip-flop to JK flip-flop, right? So if we add these connections to our basic SR flip-flop, we can derive JK flip-flop from that, and all the conditions can be verified easily. So we have already understood how to verify all the conditions, right? Now this is a change where we can make to the SR flip-flop, and we can get the JK flip-flop. So this is the circuit, or the circuit diagram for JK flip-flop. Okay. And when we verify this particular condition, we are able to verify the toggle state also. So here, the next kind of flip-flop which is used, that is toggle flip-flop, that is T flip-flop. Since we have understood that this 1 1 is the toggling state, so there are only two outputs. If J is equal to 0, K is also 0, and if let us say J is equal to 1, then K is also 1. So for 0 0, Qn may be 0 or 1. The output Qn plus 1 will be no change. And for J and K to be 1 1, Qn may be 0, Qn may be 1. Doesn't matter. The output Qn plus 1 will be 1 and 0. That means toggle. If it was 0, it will get 1. If it was 1, then it will go to 0. So there are two conditions possible, either no change or toggle. So in case of T flip-flop, which we can derive from the JK flip-flop, so no change and toggle flip-flop we can say. So so we have, for the T flip-flop, the clock is high and the clock is 0, there would be no change. Only two conditions are there, no change and toggle. Now let us discuss all the flip-flops which we have discussed. Let us revise once more. So I am making a short table for SR flip-flop. The D flip-flop. Okay. This is my SR latch. Okay. So from SR latch, we need to make the SR flip-flop. So what we are doing is, we are just adding the circuit one more, just get a clock, S and R. So the flip-flop functions, like for 0 0, it is no change. For 0 1, it is reset. For 1 0, it is set, and for 1 1, it is indefined condition, right? Now what we can do, the next part is, so here, to make the D flip-flop, what we can do, we are just the S and R flip-flop, we are connecting an inverter, and here this is the D flip-flop and the Q and Q bar, and here if D is equal to 0, the output is 0. If D is equal to 1, the output is 1. That means either it will remain in the set condition or it will remain in the reset condition. So two conditions have been removed from this, from SR flip-flop to D flip-flop. Similarly, for for this SR flip-flop and D flip-flop. Next one is the JK flip-flop and T flip-flop, right? So to make SR flip-flop, some changes we will do to the SR flip-flop, and that is going to be 3 input NAND gate, and here we are giving this extra feedback, and we can change it to the this S and R. Now we can mention it by J and K, and this will be this is Q and this is Q bar. So for JK flip-flop, we can provide an extra feedback from the output to the input, and hence we can convert this to JK flip-flop. So now this is, instead of SR, this is now JK flip-flop, and here this undefined conditions which we were getting earlier, that is now converted to the toggle state, right? So this is now my JK flip-flop. From JK flip-flop we can get the T flip-flop. T flip-flop, right? So for T flip-flop, what we can do, we can just get the this J and this K is now being shorted, and one input which has been given, that is known as T. So for T is equal to 0, there is no change, and for T is equal to 1, there is a toggle state. So this is how we can make the T flip-flop from JK flip-flop and D flip-flop from SR flip-flop. So the basic point is there are 2 conditions for T flip-flop, 2 conditions for SR flip-flop, set reset, toggle condition, and the SR flip-flop is having 4 conditions, 4 states, but 1 is invalid. JK flip-flop having 4 state, all are valid, that is no change, set, reset and toggle state. So the JK flip-flop is all these states are valid, and from that we can derive the T flip-flop. So these 4 flip-flops are very important, and these are a very consisting of so many memory elements can be designed using these flip-flop. The applications of the flip-flops are in designing the registers, okay, the counters and many more circuits which are feedback or memory dependent circuits. Thank you.